Hello, my name is Luke Raymond, and this is my Physics 2211 lab on the world's largest rope swing. The purpose of this lab is to test if the energy principle is conserved and to test if a rope can be treated as a spring. A preview of the results is that the energy principle is conserved and that you can treat the rope as a spring in the computational model. One tool I used was a closed script, and an assumption I made was that you can ignore drag force. To define the system, I chose the system as the rope, earth, and person, and the surroundings to be nothing. I also found all the initial conditions from the video and used some approximations. The main fundamental physics principle I used in this lab was Newton's second law. This helped me predict the motion of the object, or the system. And the momentum principle explains that the net force on an object is caused by the change in momentum over time. In this lab, the main forces are the force of gravity and the force of the spring. From the momentum principle, you can derive the velocity update formula and the position update formula, which update the motion of an object throughout time. The next fundamental physics principle in this lab is the energy principle, where the change in energy of a system equals the work done on the system by the surroundings plus any exchange of thermal energy between the system and the surroundings. The system should be clearly and purposely chosen when dealing with energy problems, because the objects in the system impact which types of energies are present, and objects in the surroundings impact the work being done on the system. These are the types of energies in this lab: spring potential energy, gravitational potential energy, and kinetic energy. Translational kinetic energy. Here's the experiment. And there you can see the rope is tight. So the experimental details, we began by downloading the experimental video. Then I got the initial values from the video. Then I created a computational model to predict the motion. And then I analyzed the results. So here's the beginning of my computational model, where I created the visualization setup so that you could see a picture of the motion of the system. And here's where I inputted initial values into my code and calculated the initial energies. And here's where I created a while loop to update the motion of the object over time. I also updated the energies, which then I put into my graph. Here's the result of my code. On the left, you can see the model, and on the right, you can see the graph of energy versus time. So some possible sources of error are that the simulation did not include air resistance, so results may differ from real-world behavior. This model also did not simulate the free fall phase before the rope became taut. Both the person's mass and the rope spring constant were based on approximate values, since the video didn't tell us them. So, what if air resistance were included in the model? Well, then mechanical energy would not be conserved. Energy would decrease over time. The swing height and speed would gradually reduce, and the system would experience damped motion and eventually stop. Energy would be lost due to work by the drag force, so the change in the system's energy would be less than zero. Real swings slow down because of air resistance, which is not shown in our ideal computational model. So what does it mean? For the model system, is the energy principle satisfied? Yes, because we did not include air resistance, the energy principle is satisfied because there's nothing in the surroundings, so no work is being done. This means that the total energy of the system is conserved and constant, and that the change in total energy is zero. This is also shown by the energy versus time plot. So in conclusion, the energy principle holds true, as the total energy of the system remains conserved. A spring can effectively model a rope swing to simulate real-world motion under extreme conditions. And that is the end. Thank you for watching.